in the second part of introduction to Fortran, last through very nicely covered and if you not last time, we'll go to the website and check out the slides from last week's presentation. This part I'm continuing building from the last week's presentation, and we introduce more Fortran features here. Last week, modern features will be something from Fortran 90 all the way to the latest Fortran standards. And for the organization and style, this includes free format as opposed to fixed format in Fortran 77. So we might just, if you write Fortran code, you might as well forget such thing as fixed format and go with free format. And this is a really substantive new features. For implicit none, and we mentioned a bit about for the profit model using time, and quickly to more updated feature of Fortran 90 and 95 with derived types, and we'll cover all of this array operations and the array, and we'll talk procedure and operators. And Fortran pointer is also part of the Fortran 90, but I don't will get to the presentation. But there will be another presentation more on the Fortran 2003, more of these features, and we'll have Fortran pointers included there later on this semester. And on the right side of the column here, the Fortran 2003 built even more oriented features from Fortran 90 to 95. Also, as you see, I will not be talking about I/O or I/O in Fortran. There will be talk that this I/O in SPC, in C, and probably even how to use parallel I/O, and that's not necessarily language specific. We have something like MPI I/O and more structured like HDF5 that's suitable for high performance I/O. Let's keep I/O for now, and one of the features that Fortran is really array. What is array? Array is just simply a collection of values of certain types. It can be integer, real, and other intrinsic types. And as we'll see later, you can have user defined as an array too, and it indexed by array index. Array statically allocated, where statically the size and the shape of the array has to be known at compile time. But array is more flexible, that you can you don't have the shape of the array at compile time. So the point here is that the majority of intrinsic functions, that is function and that are defined by the Fortran standard, support array argument. We'll see later this is very easy to have that. And Fortran support true multidimensional array. This is as opposed to, for example, C and C++, where multidimensional array is implemented really as an array of arrays. So this is a vector of pointers where each element points to another source where defined. So the problem here is that the array in C and C++, for example, will not be in continuous memory block. And for high performance operation, contiguous memory block is more efficient than array of pointers, array of vectors of pointers. So, and all has the support here extends to many things, many other operations that can be done. We see it later. So let's have some terminology. So the array is the number of dimensions array. So for 2008, the maximum range to be 31. So you can have 31 dimensions array. previously the maximum was 7 by Fortran 90, so maybe some compiler is not really up to 31, but at minimum you can get 7-dimensional array. The number element in its dimension is called span of the array. And depth of the array is really a factor where element of the factor is spent in the corresponding dimension. And this will be used. So let's just go into an example. Here's an example of array and array syntax. How an array is simply with attribute dimension, and here I give it the size directly. So this will be a statically allocated array where the size array has to be known as compile time. So here I define A and B to be one-dimensional array of type 10, C and D to be two-dimensional array. B is a four-dimensional array, and by default, array in Fortran starts with the index from 1 to the end of the array, but I can also change in the relation the lower of the array. So here I define array E to have lower bound of 0 and, for the first dimension, and lower bound of 3 in the second dimension, and lower and then using the default lower bound of 1 in the fourth and fifth dimension. So this will have 5 elements in the first dimension, second dimension, and 7 and 9 elements for the third dimension. Expression. You can simply just do A equals B. So this means for A of A, it will be equal each element of B. Same thing with multidimensional array. One thing we note here is that for each element, the array has to be conformable. It means the size and dimension or the shape to agree. So array is equivalent to line 7, where A equals to B. Line here, I align the fourth and the fifth element of B to the second and the third element of A. Again, the extent here is conformable. And similarly, I assign all the 10 elements of the second dimension of C to A. So this kind of array expression you can do. And A to the scalar X. This means all the value of A will have the value X, and X is just a scalar, not an array. And similarly for C. Here's an interesting example. Equal B for the first 5 elements, and also do cosine of array C from element 6 to 10 and the first dimension. So this gives you a one-dimensional array with size 5. It is I take the cosine of multiplied by B and assign it to B. So you can do this kind of a complicated array expression. You can so the array B from first element by 2 and the upper bound is 5. So A1 here will be equal to B1, A2 is equal to B3 since B is starting by 2, and A3 here is equal to B5. And there's a function called shape. This is the shape of the array, and if you print the shape of E, as I mentioned here, it will print 5, 6, 7, 9. This is 5 and 6 elements, 7 and 9 elements. So construct array is something called array constructor. So declare it right away. So you can declare array with 3 and equal this. This will be the value of you can executable statement. Same thing here, you can also declare it with some kind of a implicit do loop. So this line means that for array B, I is the counter from 1 to 5. I take square root of I and then assign it to B. One thing that A has the size of 5, X is the size of 3, then assign X, element of A will have 0, 1, 2, and will have 3 and 4. So here I use another array as part of this constructor. So now dynamically allocated array. So array can be dynamically allocated at runtime to give you more flexible size for things that you do not know at home outside. Dynamically allocated on the heap rather than on the stack array. And yes, the size of the stack is often limited to 2 gigabytes by default, and this is very much platform dependent and compiler dependent, and there is to go around that. But are not portable and somewhat problematic. So the question is, if you have a large array, always use this allocate array. The allocation is done with allocate and the allocate statement. And something that to here is the allocation, and the allocation takes time. So you don't want to have an allocate in a loop. And when you do programming, sometimes the size of the array changes, and if you keep calling this function with different size, to allocate with the larger size or the maximum size, so that you don't have to allocate and deallocate every time the size changes, because that takes time and takes time from your computation. You have to do dynamically allocate the array. Claim, rather than trying to size, I just use column, and the number of comma and column just specify the rank of the array, so this is 3-dimensional array. Now this is allocatable to tell us the compiler that this is a 4-shape array. We will allocate it at one time. So in this case, I can ask the size of the array. So user will input 3 numbers, and I use 3 numbers to allocate A, B, and that will be the size of the array, and that will be the size of the array. The size 23D is a print back size, G size, and K. At the end, so you stop using the array, you need to deallocate the array in the memory space used by this array. Array construct. So array construct is used when we want to make selective statement assignment to array. So here's an example. Suppose I have A and another array for the reciprocal of A. So if A is 0, I do not want to for A, because that will be undefined. So here, where A not equal to 0, the reciprocal A is 1 over A. Reciprocal of A is 1. So here automatically it will go to all the elements of A, and for elements of A where it does not equal to 0, it will do this code block here. That's where it will do this code block here. So for after A is 0, the reciprocal of A equals 1. Is in your condition has a probable the same shape as the array in your statement here, and the code executes when the condition is true. Another array that we use is the for mechanism to specify an index parallel assignment to an array. For example, if you have this do loop where you go through the even of this 2-dimensional array and assign the value I plus k, change this with for I from 1 to n and 1 to m. You assign type H element. So the nice thing about for all is that if you use for all and where, as we can guess, you can replace the where with this do loop and an if statement inside of the where. But then for and where tells the compiler exactly what you want to do, and it's an architecture. It will association and parallelism. In fact, these two constructs come from where Fortran was used in the factor machine. If any of you with the earlier Cray machine as a factor machine, with you simply can execute this in basically one instruction. Where if it has two loops, then the code has to execute basically an iteration. So there will be more than one instruction. In fact, there could be as many as the number of iterations here to execute this. And again, this on a support factorization or factor machine can be executed in one step. This is optimization. And even on the scalar machine, this is because for all and where is more restrictive than do loop, it tells compilers that there will be no branching, or the branching will be predictable, and it will aid operation. And also kind of construct, you notice it's more narrow and more similar to the kind of a set and found in mathematics. Notable Fortran version, for example, will be any true if any array elements are true. So you do something like this. You have array where elements. I can say if any a, meaning if I found any of the elements to be less than 0, it executes this statement. So in this case, this statement is executed because we have minus. So an array of, if you will, there is a which is array equivalence of n. In this case, the function of returns true if all array elements are true. So you can define if you have this array A, for example, and if A is greater than 0, then this block is executed. In this case, this block will not be executed. I cannot say, well, I want whether all A equal to B. So if all A not equal to B, then B are mutually exclusive. So in this case, this statement is executed because as you can see, all A not equal to B. As array to subroutine. So called assumed shared array. So let's put the terminology here. A dummy argument is the name of the argument in a subroutine. So the dummy argument, suppose we have a subroutine example 2, there's 3 arguments, A, B, and X. So a dummy argument take off an actual argument. So here U, V, and W is, and this function example 2, and I'm passing this array. So this shared array of this takes the shape of the actual argument. So in this subroutine, I do not need to know type of the arguments. Here I just say the dimension of A is column. I just tell it it's of dimension 1, but I do not know the size. And if B, I say I want B to have lower bound of 0. So it doesn't matter what's the actual lower bound of B, when it's going to this subroutine, B has lower bound of 0. And similar, I want X here to have the lower bound of 2, and to have default lower bound, so 1. So it matters what's the actual argument inside of this subroutine x has a lower bound of 2 for the first dimension and lower bound of 1 for the second dimension. So in this function, I pass u becomes a, and the size of u and a will be equal inside of this subroutine, and we'll have a lower bound of 0 b inside of this subroutine. And instead of calling this subroutine with all value of w, I have a section. So it's an extent of 5. So inside of this subroutine, from 2 to 7, and x will, the dimension will be from 1 to 5. So inside of the subroutine, the extent of the array is determined from the actual extent of the actual argument, except the default lower bound can be defined. To create array is called an arithmetic array. In this case, an array will be created upon entry to a procedure and send queries and determine at runtime. So it's just almost like allocatable, it's a need to allocate it. And here array is allocated on the stack. So let's take a look at this example. Suppose a routine that swaps A and B. I don't know and B and it can call with array of any type. And a new intermediate array called work as temporary workspace. So declare work to have the subroutine. So when the subroutine is called, work is created, and it's typically created with the size of A, whatever A is. So he use work for A because this is comparable A equals B, and then I can work back to B. So I'm swapping the content of A and B.
Does the argument A and B can be moved to the next? So they have to be one.
In this, the argument of A and B has to be one dimensional because I think the dimension to be more. Now, I shall discuss. You can overload this subroutine to have to be able to accept arguments of different dimensions. Another way to be able to accept argument of different dimensions using which we will discuss next. So one thing to note is that this kind of thing requires an explicit interface of the procedure of the subroutine. Now we'll talk about when we discuss modules, and we'll talk about this what it means to have explicit interface. Okay, elemental procedure. So we discuss function and subroutine, and this function or subroutine is a procedure. Procedure in Fortran can be declared as elemental. So elements, the procedure can be passed an array of any dimension. Of course, some restriction on how to do that. So in an elemental procedure, the argument of the array argument, the element of the array is acted upon an element at a time. And the restriction is that the argument and result in a function must be scalar, declared as scalar. And this also have to, the procedure must also have an explicit interface, and we'll talk about this later in module. So the procedure must be pure, and this means that it has no side effect. So meaning if you pass an argument, you cannot modify and for you can only return a value. You cannot modify the argument of the function. For subroutines, you provide if you declare the argument as int and out or int and in. So while intermediate function in Fortran and all elemental. We use this function circumference, and you just add a new attribute. I call it elemental. Since I do this, I can call this with an array. Let's define also another function for area and another elemental. Let's look at an example. Ignore definition for now. We'll talk about modules later on, but this is required for elemental. Here the argument is declared as scalar R, and with the result is the circumference, the scalar C. Similarly with the area, this is a subroutine just for a different example. And in argument, the input is a scalar, and the output, the intent out, meaning I can modify A inside, is also just a scalar. Suppose I have a circle, and of one radius, I have an array of radius R, and of radius, and I'm going to use A to store area, and I can call the function circumference with R as an array and as an argument. And this can only be done because I declare circumference to be elemental. So what happens here? I'm going to code. If I run, the result is for each element or the circumference for each element of the radius. Similarly, all the area with R and put the result in the first A, and if I print A, the result of each element of the circumference is printed out. The element of really in the sense that you can just write a function with scalar argument and pass an argument of any dimensional array. So R can be more than one dimension, can be as many dimensions as you want. And actually, in Fortran, elemental function or elemental subroutine can be executed in parallel, and that's compiler can get optimization. More often it is known as elemental in principle, it can run in parallel to compute the result, to execute the flow part of each element. Okay, so moving on to a derived type. This is a new feature in Fortran 90. So the type is a collection of intrinsic data types in a structure. So you can hold static and allocatable array in derived data type, and you can also hold another type. The first declare before it can be used. So here's an example of derived. Suppose I want to new type called color. Color a shade. It has the RGB value, and I declare as a array with size 3, red, green, and blue, and I want to give a name to the color. So this is how I declare. Now, after I declare the derived type, I can use it. I use any other intrinsic type, like integer or real. But in this case, I say type color and background. Background is the name of color. So how do I access this? Is using this percent sign. So I can access element of my derived type. So I assign background shade equals 10, and here I use the array constructor and I assign it in. And I print background, it will print the shape, RGB, and the name. And the place is not standard. So if to be portable, you really need to print it of the Jira type. So project function and subroutine Jira type as argument and result. And you just use Jira type just like in easy type. So you can arrays of Jira type. You can make a elemental subroutine. You can set arrays of Jira type. Okay, so step back a little bit. Why you use subprogram in this thing subroutine? Organization, when you write a program, you don't want to just have one super main. You have just one main process everything. You want to decompose complex tasks into simpler manageable code. That's why you have function to do specific things, you have subroutine to do specific things. And main program you call different functions to different subroutines. So this allows you to enable reuse of code. You can call function with different data. You can call another subroutine with different arguments, and basically that's the same thing. This also code duplication. So you can you have this or subroutines you hide implementation detail. Right? And then you limit the scope of variables. You know the variable inside the function only when you enter the function and disappear after you get out. So this for now we have function and the use is just another and in fact more flexible tool to organize code. So modules definitions that can be made accessible to other programs. In this case, another modules or another main program, and another function or another procedure or something. So module can contain Jira type and variable and variable definition. It can contain subroutines and functions. And basically, you use modules if you want to collect related type definitions, subroutine, and functions into a package that can be easily reused by other programs. So, go ahead. Yes, module can contain another module, and it's not in that if you have different concepts and you include, you literally just content of another file and dump it in those files, and you use modules, you actually just getting access to the subroutines in that. So it's not an include separate. And we'll see in the example. So go back to your here. You had elemental. So I put this function circumference, element function circumference inside the module, and I call it geometry. So say I also want to declare a new derived type. I call it circle type. Circle radius. I want to center, for example, to tell you where in your coordinate system the center of the circle is. So we declare a derived type called circle type, and you can, and then you to have a method to compute the circumference of a circle. So all of it related to the geometry of the circle. So it logically makes sense to have a module called geometry. So in this case, the implicit as we discussed before will only be the module, and this This is across all the function or across all the definitions inside the module. So the here is declaration for types and variables. There's contains, and after that you have the function and substitute definition. In this case, I have an attribute private, so by default, everything in this module is private. So for example, I declare a parameter called pi as -1, which is mathematical definition. So this program outside this module cannot see pi, but any other routine or function inside of this module can see pi. Here I declare circle type to be public, so circle to this type is accessible by other modules or other subprograms. So how or when to use modules? So the public entities of the module is accessible to other programs via use statement, and use is how you use the module, as we see as example. So module, because it provides a more reliable mechanism for specifying variables, specifying text definition, and procedure. And module facilitates a more object-oriented concept. And if it's not object-oriented, it facilitates more of a modular programming. Give you information hiding that you can private and protected entities. And by information, you can, for example, have private entities so that you need to access inside of the module can be accessible from outside of the module, and that prevents accidental alteration of internal data. So this is what is the most important feature for program organization in modern Fortran. So I really recommend use modules, and it automatically provides explicit interface. So even if you don't write your main program, for example, in Fortran, there is really to just put everything in the modules because the overhead is really low or not, and it simply just gives you a more organized and modular way to do programming in Fortran. Talk a bit about we mentioned it several times: implicit and explicit interface. So implicit, which is all you have in Fortran up to Fortran 77, you have subroutines and you have a call to subroutines, but the only available in the compiler is the position of the argument to procedure. So during linking, this the position is met and resolved. So you don't have compile time attack. So you can have a mismatch of precision and have a mismatch of type, and it may compile and link without error. When you run it, you get strange program behavior. You can get implementation fault, or you can get some weak results that's very hard to do. Because the programmer here is responsible for setting the interface.
The compiler flag, like the WO, warning.
Implicit interface?
Yeah, on the compiler can maybe something or the that you know what you're doing.
The problem is because there is no information in the compiler, or it's more to the linker, and it really cannot do anything. It really just making the symbol. And the symbols have the information of the final argument. So
The compiler assumes that you know what you're doing.
yes, it has no clue. It has no clue that you calling something. It doesn't have enough information to be able to match with it. So if I'm doing MPI the MPI right now, as MPI binding plan is really like Fortran 77. And then MPI and subroutines that requires you to use 60-bit integer. And it means that, and you just use the default integer. Your program will run, will compile and link, but you make some weird results with MPI. In fact, that's one of the annoying things with MPI for Fortran binding. So like the latest MPI standard has a Fortran 2003 which fixes implicit interface issue. The implicit interface, on the other hand, provides the compiler. You provide task, decision, argument names, and this is automatically provided when you put your procedures in a module. And so to have explicit interface, it is wrapped into a module. So it has to be compiled first, so the order of compilation is dependent, and that will give you usually .mod file. Will give the compiler information, give you tagging and name matching for everything. The basic is that the compiler can do consistency tagging. And in fact, explicit interface is required for many features of modern Fortran. So you can have optional argument, optional parameters, elemental procedures as we discussed before. And for process overloading and that kind of thing, we need explicit interface. So I'll use explicit interface. Now, programming, this is a lot harder because then you use different compilers. But Fortran programming, there's no reason not to use explicit interface. So, I want to do a live example here to just put all the things that we've discussed so far, derived type, modules, and subroutines, and also subroutines, and the use module. So I want to do some geometry test. First, I have what you call numeric. We discussed how we do time to do numeric. So here I have a module that declare or define what kind of precision I want. And in fact, I provide a name constant for various precision. So before I have implicit none, and by default I want everything here to be private. So I declare others means that the value will be constant, and I set it to public, and I name it KSR time single precision integer, and it has to have 4 digits, and so I have to select it in time 4. And then we want to have a time default integer. This is so I just take them out the integer on this machine. So I just use the as default. And similarly, I have long integers, so I have selected integer kind 16. And here to have single precision real, so I just do kind of 1 point, which is kind of a real number. This platform. The double precision, I just do kind of 1 to P0, which is the double of the lexical of the double precision. And suppose I want to have a quadruple precision, then I just multiply the precision of my precision integers and use that as an argument of the selector. So here I have all the nice names value for precision. The nice thing about this is in the future you want to change precision to edit this one module and build your code to compile your code and you change all the precision in all your code in a portable way. So Here somebody declare color just to have a type of color. Of course, it's just a trivial example. So I use numeric precision with the module I just declare for the precision, and all of my real I declare it as precision. So here real R meaning this real has single precision and the integer has default precision. Just but the here is I use the module numeric precision that that before.
I'm sorry, this is the module was defined in a single file by itself. So you should want to define a module per file. You don't have multiple modules.
Yes. You can have multiple modules in one, but a good practice will be to have one module per file.
Previously, in the sequence example, the module was defined next to the function, right?
The module are next to the program. So it makes module and program the same file, but that's I did that much everything on one screen, but again, a good practice would be use your main program standalone in a file, and you have one module per file. So here I have one module per file. Geometry module. Choose numeric precision, which is the precision of the real, and use color. So now since I use color, I have access to the color. So here this type. And in this module, I put all my subroutine and function related to the geometry. So here I have the circle area and make it public because by default I have it as private. So I make it public so that it's accessible by other programs. So, and this is previously, as you previously so the GeoF is main program geometry test use the numeric precision to give me access to the real and the precision. I guess I don't really need it because I don't use any real. And I geometry that gives me access to the circle type, which I use to declare this very circle as a array with size define later input. So here I use it to enter the number of circles, and knowing this number, I allocate the array model, and for each of the ask the user to enter the circle radius, and then circumference is defined in the geo modules, and circumference is elemental. I just call it with one line circumference model as an array argument, and I call area as my circle, and I deallocate my circle to remove the memory usage.
Uncertainly.
Oh, and for code continuity. N% is I did not go through that.
Why you wrote the code letter in your...
Yeah, it's a matter of style. Okay. You can do all this way. You can do this way, but I have different with parentheses and code blocks. So my regular style is to have the type and then column and line and then for all the parentheses and all attributes. So just it's really useful. But import to one file and see consistent with it. Okay, okay. Thank you. So, order of compilation here is important because numeric precision is the module that does not use any other module. You need to compile that first. Import numeric precision. And then precision is, and then to use numeric precision, and is used by geometry. So color is that. Now we have, yeah, but mod file is not part of the one thing to know, the mod file is not really part of the standard Fortran. It's just many compilers just to do that. But the great compiler, it's a thing into the software. So we are not the two about what is doing, but the main point here is that the order of the compilation is important.
So I here you have, for example, color, you have two files, not all,
yes.
not
yes. The module here is the module information, not all the virtual software that you use to review. So, geometry use so in case when geometry use numeric precision, because we looked this particular compiler is so whether there is numeric precision mod that has the information of numeric precision module. But again, part of the standard, and we should be agnostic about it. So I need to compile geometry precision and color, and everything has been compiled before, and compile the program and all the objects are equal. Yes. And what if you want to do it in a so simply just link this and or copy this and then you link it. Make file. This is a simple example you can do by hand. Okay, now we have the geometry test C. You look at the number of circles, 5, and the time to 1.0, 2.0, 3.4.4, 4.5, and the circumference and so you can do very sophisticated programming and build a very large code base using a modular type programming. So very, very useful and very, very important.
For that example,
yes.
So you have program in a single or you have to go line by line?
Yes, because the order of compilation is important. Yes. Even so if you want to use, for example, in geometry, if I want to use numeric precision, the numeric precision contains numeric precision module has to have first before this one. Because this module needs the information able to use numeric precision. So if this again, this and before here I use color type. Color type, the type has to be available. So they're accessible from the module type. So using this, let's extend the capability. You can do cross overloading, and so often really allows several procedures to be called by the same generic name. So if you implement different variations of same basic concept while implementation detail. So in oriented principle, this is known as polymorphism. So as an example, before so the area of any object has the same basic concept but computed differently. Of course, if you in the abstract level in calculus, the type of area can be as the area of the curve. But then let's just take from the perspective of geometrical perspective, circle, rectangle, and triangle all have the same area, but the point to compute them are different. And of course, circle, rectangle, and triangle only needs the width, and rectangle needs the width and the length, and the triangle probably needs the width and the height. Yes. So procedures if at least one of its arguments is distinguishable. So anything that can make the compiler distinguish procedure works. So you can have different precision, you can have different array shape, and you can have different types. So let's look at how we can do a generic interface. On this geometry module, everything else to say, let's look at geometry. So here type or rectangle type has the width and the length. And skip the I have private subroutine for circumference of a circle and circumference of a rectangle. And I want this to be referred to as circumference. So publicly named subroutine is called circumference. Privately named subroutine is the circumference, circle, and triangle. So here is in something called the module interface. The interface name is circumference, and the circumference is overloaded to circumference circle and to circumference triangle or rectangle. So if you look at the circumference circle, where you really compute it with 2 for pi r, and circumference rectangle with the formula is 2 equal 2 times length width. And here is the circumference of a circle type as an argument, and circumference of rectangle. So I will example available later, but you can look at the other things. Here I have initialized random circle and initialized random rectangle, and public name is initialized random, and all display is just needed to display the circle and rectangle. So I will not go through the details, but the point here is that from our module, I only have 4 subroutines or 4 names: initialized random, circumference, area, and display. So let's use this. So suppose I have a program called geometry system. I have a circle, and I just make this before, but rather initializing radius one at a time, I just initialize random, which basically just initializing the radius by random number, and get the circumference of this object is by calling circumference object. And since the compiler knows that the object is of circle type, it automatically reroutes this call to the terms of subsequent. So a call goes here if the argument is circle. So another code called geometry rectangle. This is really the same code. The only difference is that now the object is a rectangle. To get the source of this object, I also call circumference. Notice the name is the same because circumference is the same, because circumference is overloaded. But in this case, the callers know that circumference of a rectangle goes to the circumference rectangle. So I can automatically reroute this function to height. So look at this and create about the rectangle, which is just give you the width. The here. Enter circle. The circle, I will get the radius and compute the circumference of the circle using different factors. This is very nice because you can imagine you can extend this any other type of geometry. In fact, a better way to do this is that surface works across modules in different parts. So you can imagine you have one module in one part for circle, another module in another part for rectangle, and do the offloading across the two different modules. And it's scalable programming because then you can imagine if you have different type of object, you can have 10 people work on different parts and different modules. All they have to agree is the name of the generator. And here you can have scalable programming and you can extend it as you need it. And in fact, this kind of program can imagine if you geometry, you overload the geometry in certain way, and if you work in other type of geometry, in Riemannian geometry, you do different formula, and all can have the same generator. One, the operator, the intrinsic operator in Fortran can also be operated. So here the intrinsic operator plus, minus, division, and assignment can be overloaded. So, as an example, I want to overload the intrinsic operator plus. I want to make a circle sum. So I say interface operator plus circle sum, and I define my own way to do the sum of a circle. So let's just say I want to say the sum of a circle is just the sum of its radius. So if I can call this, I can have object of a circle C1, C2, and C3, and I can do C1 plus C2, and plus here I will define class to be the sum of radius of C and C2, and assign it to the radius of C2. So here also you can imagine you can overload the operator for object, for matrices, for vectors. So you can have, say, if you're familiar with abstract algebra, where you, in group theory, where you declare different types of operators to have different meaning in different groups, Fortran completely support all of this. We'll close with just some best practices in Fortran programming. Take advantage of the free format. Use space notation, line break as necessary. Choose star and be consistent with it. Use comments as necessary. This fixed format is you want to use Fortran. Every time using this non, in modules to get the explicit interface. Even if it's better to put everything in the module in the really low. And write module-oriented code basically. And this related to before, you create one part of module, use module for information housing in the case of the overloading. Someone to know how to really use the circumference of a certain length object, but all they need to know is really just interface with that uh, circumference region. So this is scalable programming. Use module variables and common blocks judiciously because they both a global variable and they are not static. So use to organize your data and you derive types and related methods in a module. You can for subroutine argument and as much as you can use your function. Function should not have type effect and allow you to use to have element of function. Portable precision module using with time. And just we discuss almost everything on this left-hand side here. The only thing I'm missing is the Fortran pointer, and we'll discuss that when we talk more about the Fortran 2003 in a future session. So that I will entertain any questions you may have.